And given any continuum space-time, mg, there exist causal sets, C, and this less than sign stands for the order relation, C less than, or C precedes, which the continuum manifold approximates. So given any continuum space-time, there are causal sets that can underlie that continuum space-time. There are causal sets which encode the continuum geometry well enough so that you can say the continuum is an approximation to it. And strictly speaking, that's a conjecture in causal set theory for which we have by now a lot of accumulated evidence. However, most causal sets are not manifold-like in this way. If you just pull a causal set, a large causal set, so let's say of 10 to the 240 elements, out of a bag of all causal sets of 10 to the 240 elements, then it will look nothing like a manifold. So most causal sets are not manifold-like. They have nothing, they don't have a continuum approximation. Okay, so that allows us to construct a causal set which can make sense of the idea of before, even when general relativity breaks down. So this is an example. So this, I'm going to give a series of 3 examples. So this is example 1. This is an example of a causal set in which the universe has a beginning, there's a big bang, and one continuum epoch, let's say our approximately FRW spacetime. So the causal set is represented by this orange blob here. It's Hasse diagram-like in the sense that the past is down at the bottom and the future is up at the top. So down here is before and up here is after. And this causal set has a number of minimal elements, or they could just be 1. And on top of those minimal elements, there's a portion of the causal set which is not manifold-like. Some non-manifold-like business is going on. And then there is some either region of the slab of the causal set, or maybe a single anti-chain of unrelated elements, which stands for the Big Bang, after which the causal set is such that it's well approximated by a continuum spacetime, say an FRW spacetime. So this is one individual causal set which has these different regions. There's the level of minimal elements, which is the beginning. There's a bunch of stuff happening which is in the deep theory, which has no manifold-like interpretation. There's a transition, let's say, which is designated by the Big Bang, between that non-manifold-like deep stuff and the epoch of the continuum epoch, which is approximated by a continuum. Okay, so that's possible. We can construct such causal sets. The second example is a bouncing universe with a beginning and with many epochs. And here I want to stress that the ground set is the natural numbers. And this orange thing, again, is the causal set, single causal set. And there's one minimal element of the causal set, and that is 0. That's the number 0. So the ground and all the other elements of the causal set are the other natural numbers greater than 0. So that's the origin. Again, this region of the causal set inside this rectangle is a continuum epoch. Let's say it's approximated by some continuum manifold mg. And between the origin and the beginning of the continuum epoch, there's again some non-manifold-like causal set stuff going on here. It transitions at a Big Bang hypersurface into this continuum epoch. And then there's a big later on, there's a big crunch. So another hypersurface, another transition between continuum epoch and non-manifold-like epoch that ends in, again, a single causal set element. And that's known in the mathematics literature as a post. It's an element in a partial order such that all other elements are either before it or after it, or they're either below it or above it. So this element here is a post. And then after the post, there's another non-manifold-like era. Then there's a continuum epoch ending in a big crunch, and there's a non-manifold-like bit ending in a post, and then the post blows up again into a non-manifold-like era, and so on. So that's another causal set that we can construct. So and I should mention here, in this causal set, every event or every element of the causal set has a finite past. So let me choose an element in this continuum epoch here. How many elements does it have in its past? Well, its past includes the post, and between it and the post, there'll be finitely many elements because this is a locally finite partial order. And then between this post and that post, again, there are finitely many elements in here. So each epoch from post to post has finitely many elements. So every element of the causal set has a finite past. This is a past finite causal set. And that is, I'm going to use that as being synonymous with the universe has a beginning. The causal set is past finite. Every element has a finite past. That means the universe has a beginning. And that's also synonymous with the ground set being the natural numbers. These are all the same. Saying that the ground set is the natural numbers is the same thing as saying that every event has a finite past. Right. Now this picture is almost the same as the one before, except this is a bouncing universe with no beginning. So here's a post, but it's not the beginning. It has a past. So this causal set stretches up into the infinite future and down to the infinite past. In this case, every event has an infinite past. There's just an infinite set of continuum epochs, each one beginning in a big bang, ending in a big crunch, with posts in between them all. And in this case, the ground set is Z, the whole of the integers. So this post, for example, in the middle here, that could be 0. And then all the elements down below will be the negative integers, and all of the elements above that post will be the positive integers. So in this case, every event has an infinite past. However, in this case, the ground set is Z. However, it's not the case that those are synonymous. There can be causal sets whose ground set is Z, but in which every event doesn't have an infinite past. So for example, you could just have an infinite anti-chain. That's just a countable number of disconnected elements. They could just be the integers. So that's a causal set with an infinite causal set with ground set the integers, but every event doesn't have any past or future at all. So it certainly is not, it's not past infinite. So this causal set that I've depicted is past infinite, and its ground set is Z, the integers. Okay, so let me summarize so far. I've just talked about kinematics, just causal sets that you could just write down. Well, not the infinite ones, but the causal set paradigm has a structure to accommodate universes with continuum regions and deep structure regions that resolve singularities in the continuum theory. Universes that have a beginning, whose ground set is the natural numbers. universes that do not have a beginning, whose ground set is the integers, universes that undergo cycles of expansion and collapse, continuum epochs punctuated by continuum singularities. So I just want to stress the regions of the causal set which are not manifold-like, they correspond to singularities in the continuum theory. They can't be, they're not included in general relativity. General relativity doesn't describe those. And I can't resist mentioning universes where a black hole singularity, which you can think of as a localized big crunch, is followed by a new continuum epoch or baby universe in a sort of realization of the idea of cosmic natural selection, Lee Smolin's idea of cosmic natural selection. And in all of these cases, the causal order of the causal set, this notion, fundamental notion of before and after, allows sense to be made of one thing after another. So it's the structure of the epochs following on one after the other is accommodated, is allowed, is natural in the causal set structure. Right, well, that's all very nice, but are these models physical?